Thank you for the invitation. Okay, so let's write the title. I will convince you that torsion groups do not act without a global fixed point on two-dimensional cat-zero complexes. So this answers partially Mladen's question 2.11. Happy birthday. And this is joint work with Sergey Norin and Damian Osajda. Okay, so let's first set up the space, which will be of interest to us. So what is this two-dimensional cat-zero complex? So the space X today will be a piecewise Euclidean two-dimensional simplicial complex, two-dimensional simplicial complex with finitely many isometry types of simplices. With finitely many isometry types of simplices. And now to formulate what it means to be cat-zero, we look at links of vertices. So for V, a vertex of the complex X, we define the link of V. Okay, what it is, we look at the vertex V, like we look at all the cells incident to V. Okay, maybe there are 6, say 7 triangles incident to V. And then the link is the graph with the vertex set V in correspondence with the edges in the complex X incident to V. So for each edge incident to V, we pick one vertex in our link. And the edges of the link correspond to triangles incident to V. So for every triangle incident to V, we put an edge in our link. So eventually, our link of a vertex is a graph. And it's a metric graph. We equip this graph with the angular metric. What it means is that if you have here a white triangle incident to the vertex V with angle alpha, we equip the corresponding blue edge also with length alpha. So this allows us to talk about these link graphs, and we say that X is cat-zero if it is simply connected and for each vertex V in our space, all cycles in the link have length, this angular length, at least 2 pi. So these are the spaces that we are discussing. And the theorem that we will prove with Norin and Osajda, call it theorem 1, is the following. Suppose we have a finitely generated group acting on that space. So let G be a finitely generated group acting on our space X by simplicial isometries, and in a non-trivial way, in the sense that without a global fixed point. Then G is not a torsion group. Then G has an element of infinite order. Then G has an element of infinite order. Let me mention for which groups this theorem was known before. So theorem 1 was known for, first of all, for G acting geometrically, so acting properly and co-compactly. This was proved by Swenson in '99, in fact, in any dimension, and also finitely presented subgroups of such G, of G acting properly and co-compactly. This was proved in dimension 2 by Hanlon and Martinez-Pedrosa in 2014. So here in our theorem, we don't need any conditions. We don't need properness, we don't need co-compactness, we don't need the assumption that the group is finitely presented. Questions? Let me show you the proof outline. So suppose that by contradiction that all elements have finite order. Suppose that each element F inside the group G has finite order. We will prove inductively the following property, property that we call Pn, which says that for each finite set of size n, F1 up to Fn, so n elements of the group G, if you look at the intersection of fixed point sets of these elements, so fixed point set of F1 intersected, etc., intersected with the fixed point set of Fn, is non-empty. So once we get to the number of generators, our group is finitely generated, we'll know the fixed point sets of all the generators intersect, so it means there is a global fixed point. So let's see how to prove these properties. So first of all, P1 follows from the fixed point theorem for cut zero spaces. we have a finite order element, it generates a finite group, so it has a fixed point in the space. So this means that each single of these fixed point sets is non-empty. So P1 follows from the cat0 fixed point theorem for finite groups. Let me skip the intermediate steps. Suppose we have already proved P3. This will imply P4 and actually P5, etc. Let's call it P greater than 3. This follows from the Helly theorem for cat0 spaces, from the Helly theorem for cat0 spaces. This was proved by Sergey Ivanov. Let me just mention, for example, how it works for the Euclidean plane. Suppose you have property P3. Suppose you have some family of sets that they intersect in triples. So say 4 sets, and I will try to draw them so that each triple intersection is non-empty. And once I do it, we see, at least in this example, so these are convex sets. And these 4 convex sets have non-empty triple intersections, but apparently if I try to draw them on the plane, all 4 of them have a common intersection point. So this is the Helly theorem. We are working in dimension 2 cat0 space, so it's similar to the Euclidean plane. So these parts of the proof are standard. They work in any dimension, and now the problem is to fill this gap from P1 to P3. We will focus on one of them because they are both similar. We will focus on the easier one. So we focus on the implication from P2 to P3. So P1, P2 is similar. Okay, so if we want to prove P3, better take 3 elements in the group. So let F, G, H be some 3-element subset of the group G. And we assumed P2, so we already have that. We have that these fixed point sets, the fixed point set of F, the fixed point set of G, and the fixed point set of H pairwise intersect. So we want to prove that they have non-empty triple intersection. Let's do it by contradiction. So assume for contradiction that if you take the triple intersection of the fixed point set of F with the fixed point set of G and the fixed point set of H, suppose this is empty. And let's draw a figure explaining what is the possible configuration of these fixed point sets. So say the fixed point set of F is somewhere here. It has to intersect the fixed point set of G, and the fixed point set of H intersects the 2 of them, but we assume that they have empty triple intersection. So what can we do with such a configuration? Well, we can, since double intersections are non-empty, we can take a point in each of the double intersections. And since these fixed point sets are connected, we can find a path in each of the fixed point sets, joining the 2 of the 3 points that we chose. So we obtain a blue triangle. So now to proceed, let's assume without loss of generality that the action of the group is without inversions. We can obtain that by passing to the barycentric subdivision. So assume without loss of generality that G acts without inversions. So whenever it stabilizes a simplex, it fixes it pointwise. Then the nice thing that happens is that these fixed point sets are subcomplexes. Then these fixed point sets of f, of g, and of h are subcomplexes. Of the space X. And then we can make this blue triangle and an image of a simplicial map into our space. So, namely, we let the delta, will be, say, blue delta, be a minimal area simplicial disk that satisfies the figure on the right. Namely, we assume that the disk comes with a decomposition of its boundary into 3 paths with a decomposition of its boundary, the boundary of the blue triangle into 3 paths, P, Q, and R, such that P is mapped into the fixed point of F, Q is mapped into the fixed point of G, and R is mapped into the fixed point of H. So we require to have a non-degenerate simplicial map, non-degenerate simplicial map psi from the triangle to the space, such that, as I mentioned, phi of P is contained in the fixed point set of F, psi of Q is contained in the fixed point set of G, and psi of R is contained in the fixed point set of H. So I just spelled out the conditions that you see on the figure. And so why does such a disk exist? Well, these 3 paths form a closed path. The space is simply connected. So using simplicial approximation, we can find here some simplicial map. So eventually this triangle will be subdivided maybe in some triangles that are actually triangles of our complex X. And minimal area means minimal number of these small triangles. And let me mention immediately where this minimality will be used. So the minimality will be used in the following lemma. It has 2 parts. So in the first part, suppose we have 2 triangles, T and P prime, inside the blue simplicial disk. Suppose they share an edge. These 2 distinct triangles share an edge. So for example, you can have this triangle as T and this triangle as T prime. If they share an edge, they map to different triangles in the complex X. Then psi of T is distinct from psi of T prime. Because if they were mapped to the same triangle, if we would have a folding, then this would mean that we could have chosen a blue disk with a smaller area. And the second part is similar if you have a single triangle inside the blue triangle that's adjacent to one of the boundary paths, say P, contains a boundary edge, say in P, then the image under psi of this triangle is not contained in the fixed point set of F. So if you have a purple triangle that's adjacent to P, it cannot be in the fixed point set because otherwise we could change the blue path. We could, instead of going up, we could go up, right, and up, and we would shrink the area of our triangle. Okay, so this is exactly how minimality of the area gets used. And there is an immediate corollary to this, signalizing the method that will be used to find an element of infinite order to get a contradiction. Namely, suppose we look at this blue simplicial disk and we remove the vertex set, delta 0. Suppose this disk has a periodic billiard trajectory. For example, these are all, say, equilateral triangles, then this would be a periodic billiard trajectory, which avoids the vertex set of the blue triangle. It avoids this vertex, for example. So suppose we have such a trajectory, call it gamma, then somewhere inside the group generated by F, G, and H, this group contains an element of infinite order. Okay, let me convince you how this corollary works, how it's proved. So this trajectory gamma wants to become a geodesic axis for the element we are searching. And thanks to the fact that the purple triangles are distinct when they are mapped by psi to the space X, this orange trajectory is a local geodesic if restricted to these pieces between hitting one boundary component of the blue triangle and another. So these three pieces that we see here are local geodesics. Let me now redraw this blue triangle. Okay, so we have this billiard trajectory. It's not a geodesic at this point, but what we can do is we can reflect. So we take the map F. The left blue edge of the triangle is in the fixed point set of F. But now when we reflect, since this purple triangle was not in the fixed point set, our trajectory here gets reflected to a trajectory that's composed with this piece is a local geodesic. And we can develop further. We can now reflect here, and we get a geodesic inside our space. And it's easy to write out a group element which preserves this geodesic. So basically the proof idea is that gamma develops to a local thanks to the lemma, and hence global by the properties of cut-zero spaces, geodesic say call it gamma tilde inside the space X minus its vertex set. And this geodesic gamma tilde, in fact, is an axis for a word, say call it W, inside the group generated by F, G, and H. And the word can be written out just by recording the order in which the orange trajectory meets the boundary of the blue triangle. Recording the order in which gamma tilde, say the original periodic trajectory gamma, meets the boundary of the blue triangle. Okay, so in particular, in this example, we hit first the side corresponding to F, G, and H, so we will have an element F, G, H that maps this edge to this one, and it preserves the entire geodesic. It acts like a glide reflection in this example. Okay, so that's why we will be looking for periodic trajectories in the blue triangle. Once we find it, you will get an element of infinite order, and this will give a contradiction. So this will mean that actually these three sets had to intersect. So how to get periodic trajectories? Well, in one case, we can use the theorem of Mazur from 86, saying that if you look now at the links of the vertices inside the blue triangle, if the lengths of all vertex links in the blue triangle are rational multiples of pi, I will write it, are commensurable with phi, are commensurable with pi, then indeed if you take the blue triangle, remove the vertex set, this surface, this billiard, has a periodic trajectory. Okay, so here we have to look at these various vertex lengths. They are circles for interior vertices, but they might be just arcs for boundary vertices. If all of these curves are rational multiples of pi, then the theorem of Mazur gives you a periodic trajectory as we want it, and this gives you an element of infinite order. So this is the end of the story in this rational case, but it turns out that you can also prove the theorem in an irrational case. So the rest of the presentation will be concentrated on the irrational case. And for that, a theorem from graph theory comes in handy. So this is our theorem 2. Theorem 2, it's again with Sergey and Damian. Suppose we have a graph gamma, a metric graph, and suppose we have a cycle in that graph. So let alpha be a map from a graph that's topologically a circle into our graph gamma, be a cycle that's immersed in our graph. And now assume the following competing conditions. First of all, assume that the condition that's implied by cat 0 for our graphs that appear as links. So assume that all cycles in gamma have length at least 2 pi. And on the other hand, assume something about the diameter of this cycle. So assume that each pair of points x and y in the image alpha of the cycle C, assume that they are at distance at most pi in the graph gamma. Maybe on the cycle they are far, but assume that once you take the image of the cycle under this immersion in our graph, assume that they are close. Then the length of alpha, is commensurable with pi. Is commensurable with pi. So some of you might know a similar theorem classifying one-dimensional buildings, that you have a graph of girth 2 pi and of diameter at most pi, then it has to be a building. So in particular, all the edge lengths are rational multiples of pi. So this is a variant where we assume less. We assume only that some cycle has diameter at most pi, and we still gain some rationality on the length of the cycle, that its length is commensurable with pi. So, and it's a surprisingly difficult theorem to prove. Luckily, we had Sergey at McGill who proved that. So let me maybe outline first how this theorem 2 allows us to finish the proof of theorem 1. So how theorem 2 implies theorem 1? Okay, so there were these two cases. Let me repeat that if the condition, this rationality condition of Mazur's theorem is satisfied, then we just apply the corollary. It suffices to use the corollary to get the periodic trajectory and then an element of infinite order, which is a contradiction. So now assume it's not satisfied. So it means that one of the vertices has a length that's not commensurable with pi. There are several types of vertices. There are these vertices. Let me redraw the blue triangle here. Okay, it is triangulated into these small triangles. And let's, to make things simpler, let's focus on a vertex that's an interior vertex of this triangle. Then this irrationality means that the length of this loop, which is the link, is a non-rational multiple of pi. For this vertex, in order to proceed with the same argument, we would have to develop. And because if this arc was not a rational multiple of pi, so would be this circle here. And similarly for the vertex of the triangle. But let's focus, for simplicity, on vertices in the interior. So suppose the length of this orange cycle is not a rational multiple of pi. Then we apply our theorem 2 exactly to the link of V and the cycle that's the image of this orange cycle at the link. So no.
So the condition is that the vertex is that something the length of the edges in the link, or the length of cycles?
So whenever we have a vertex, maybe I can in this picture. Whenever we have a vertex V, look at its link. Maybe this orange circle, maybe this orange half arc, we require that this orange curve has always is a rational multiple of pi. So now suppose the contrary, suppose there is at least one bad vertex. Look, so here I will draw the situation when this vertex is inside and the triangle. So otherwise, by theorem 2, there is a vertex V of the blue triangle and the conclusion of the theorem does not hold because the length of the link is not commensurable with pi. So this means that the second hypothesis of the theorem is contradictory. So this means that there are 2 points in the link that are farther than pi. So let's call these directions xi and eta. There's a vertex of blue triangle and directions xi, eta inside the link of V, or maybe its development if V is on the boundary, with the angle between them, between actually their images under psi in the space X, the angle between the image of xi and the image of eta is strictly larger than pi. And now I will sweep something under the rug, but I would like to just mention that using some sort of Poincare recurrence, a la Ballman and Bryn, we can find a billiard trajectory that now is almost disjoint from the vertex set of the blue triangle, but goes through the orange vertex, but in a controlled way. So we can find a billiard trajectory. Let's write it still that it's in blue triangle minus the vertex set, but it starts and ends at the orange vertex. Starting at V, close to psi, and ending also at V, close to eta. So we have these 2 directions which are supposed to be far under psi, and we can find a trajectory, billiard trajectory, which starts close to, say this is psi, this is xi, this is eta, trajectory that starts close to psi, and then after some time comes back to the vertex V close to eta. And if it's appropriately close, it's still these orange intervals, the starting and ending orange interval, are still at an angle greater than pi. So our trajectory still develops to a geodesic because at the only point of new type, these starting and outgoing orange intervals are close to directions which we know that under psi map to directions at angle larger than pi in x. So here, once we construct this orange trajectory, we just finish in the same way as before by developing. So then proceed as in the proof of corollary, as in the corollary. Okay, so this shows the implication from theorem 2, at least sketches the implication from theorem 2 to theorem 1. And now to finish the game, we need to discuss this graph theoretical result, theorem 2. And it turns out that the crucial part of this theorem is a theorem of Dane from 1903. So here's the theorem. Let R be a rectangle tiled by squares, by finitely many squares. So, okay, so here is a rectangle, and now it's tiled by squares. So, for example, say there is a blue rectangle, S1, maybe an orange rectangle, S2, maybe a purple rectangle, a purple square S3. Okay, so we have a tiling by squares of the rectangle. Then the side lengths of the rectangle R are commensurable. Are commensurable. So the ratio between the length of one side and the other is a rational number. So let me prove this for you. Maybe. Okay, no, I will need the figure. So let's keep it here. Okay, so let's give a proof. We extend all the sides of these squares, these horizontal and vertical sides of the squares, we extend them so they cut through the rectangle. So, for example, here we extend this vertical side, this horizontal side, etc. So this cuts up the rectangle into these small rectangles, and let's call the horizontal side lengths of these smaller rectangles, say, x1, x2, x3, etc., and the vertical side lengths, say, y1, y2, y3, etc. So for the proof, extending the square sides, we obtain a tiling by rectangles of side lengths. Well, the horizontal ones are called xi, and the vertical ones are called yj. And now linear algebra comes into play. So let V be the vector space generated by all these xi and yj. So that it's a vector space over the field of Q spanned by the xi's and the yj's. So now, what happens if these side lengths of the large rectangle R are not commensurable? So if x, this is the sum of xi, and y, this is the sum of yj, are not commensurable, then we have a linear functional which we can arbitrarily define on x and on y. Then there is a linear functional, call it f, from the vector space V into the field Q, and we can require any values on x and y. So suppose f on x is equal to plus 1, and f on y is equal to -1. And then, let's see what happens when we use linearity of f. Namely, let's look what is f of x times f of y. So by linearity, it's just the sum of over xi and yj, f of xi, f of yj. We just used the linearity here of f, and now we can group these pairs. So this is a sum over pairs. We can group them over the pairs that tile a given square. So for example, here we have two rectangles tiling the first square. So the first element of the new summand that I will write will consist of two terms in the example. So we sum over k. K is the number of squares. And then we sum over all rectangles of the form xi times yj in the square labeled number k. We sum this product fxi fyj. But now using linearity, we will get here that those fxi times fyj will add up to f of the horizontal length of the square times f of the vertical length of the square. So you will get the sum over k of f of the side of kth square squared. So this is non-negative, but we defined, now we have to use our choice. We defined f of x to be 1, f of y to be minus 1. So that's minus 1, and that's a contradiction. Okay, so this is how Dane proved using linear algebra that you cannot tile, you can only tile by squares a rectangle with commensurable side lengths. So to finish our story, there is only one thing that remains to be proved. Right, we are missing now the application of Dane's theorem in the proof of theorem 2. Okay, so we are missing the implication from Dane's theorem to theorem 2. But since we are out of time, I will thank you for your attention, and you can ask me a question how this follows.
Well, would anyone like to ask this or any other questions?
Yes, please.
Thank you. So see, the same theorem works if R is not a rectangle, but if R is an annulus, so a product of interval and a circle. Instead of interval times interval, if it's an interval times a circle, the same proof works. So now let me show you where is the annulus when you prove theorem 2. Namely, you have this cycle C immersed in the graph. Let me explain you what happens at least when it's embedded. This is an easier situation. We have a cycle C embedded in the graph, and then we look at the product. So the annulus is the product, is a subset of the product of C times C. So it's the subset of pairs of elements in the cycle such that the distance between x and y is greater than pi. This is the distance in the cycle. Okay, so in the cycle there is in the product, so this is C times C, there is a diagonal somewhere, and now we remove a neighborhood of the diagonal. We remove the pi neighborhood of the diagonal, and we are left with an annulus. So this is the board, and now I will have to explain you how you define squares. So remember, we assume that all elements, all points in the image of the cycle are at distance at most pi. But if you take a point inside the annulus, some point x, y, where in the cycle they are a distance larger than pi. So this means, say this is alpha of x, this is alpha of y. If they are closer in the graph, this means that there is some shortcut. So there is some shortcut. Maybe we go along a cycle for some time, then we shortcut, and again along a cycle. And this is of length at most pi by one of the conditions of theorem 2. So now a square, one of the squares in the tiling, is the set of points x and y using a fixed shortcut. So you can see that, for example, if you take this point and this point, well, the same shortcut could be used to show that they are distance smaller than pi. And in fact, if you look at all the set of pairs of points that use this particular shortcut, as a shortest path between them, you will see that you get a square. And these squares are disjoint because the girth of the graph is 2 pi, so you cannot use two different shortcuts. So these squares in this way tile the annulus, and if you make a small computation, you will see that the fact, once we prove that this annulus has non-commensurable width and length, this is exactly equivalent to saying that the length of alpha is not commensurable to pi. So this is the final touch.